In this video, we'll discuss about asymptotes. Asymptote is basically a line which approaches the given curve as one or both of x or y coordinates tend to infinity. Now, if you recall the graph of 10x, then we have drawn lines like these at pi by 2, 3 pi by 2, minus pi by 2, that is at odd multiples of pi by 2. And then we have drawn this graph. Now basically this curve and this line, they're getting closer to each other, but they'll never intersect, and this line is never going to cross this curve, and loosely speaking they'll intersect at infinite. So this line, it is an asymptote. So this is the case of y equals 10x. Another example could be the graph of y equals e to the power x. Now if we draw this graph, we know it is an increasing curve. Now if we look at this curve and x-axis, they're getting closer to each other and they appear to meet at minus infinite. So for this graph, this x-axis, it is an asymptote. So we have this asymptote in this first case. And finally, we'll consider the graph of hyperbola, which is x square upon a square minus y square upon b square equals 1. Now, to draw this graph, what you do is, we draw these two lines, which are asymptotes of hyperbola, and then we draw this graph. Now in this case, this line, which is y equals b upon ax, and this other line, which is y equals minus b upon ax, both these lines, they are getting closer to the curve, but they'll intersect the curve at plus and minus infinite. In this case, these two, they are asymptotes. So essentially, asymptote is that line which gets closer to the curve and it appears to meet the curve when one or both of x or y coordinates tend to infinity. Now we can categorize these asymptotes in two parts: rectangular asymptotes and oblique asymptotes. Now, if the asymptotes are parallel to x-axis or y-axis, so if they are parallel to x-axis or y-axis, we say they are rectangular asymptotes, and otherwise we say the asymptotes are oblique. Now in rectangular also, we have two types. First one is vertical asymptotes, and the second is horizontal asymptotes. So if a parallel to y-axis, we'll say it is a vertical asymptote, and if it is parallel to x-axis, then we say it is a horizontal asymptote. And if it is neither parallel to x-axis and nor parallel to y-axis, we'll simply say it is an oblique asymptote. Now we look at how do we find these asymptotes. First, we'll discuss how to find horizontal asymptotes. Now basically finding horizontal asymptotes is easy, because in this case, this line, it appears to meet the curve at either plus infinite or minus infinite. So for this, what we'll do is we'll calculate these two limits. Limit x tends to infinite fx and limit x tends to minus infinite fx. If these limits, they exist finitely, say L, then we'll say this line y equals to L is a horizontal asymptote. In the same way, if this is say L dash, then we'll say this y equals L dash is a horizontal asymptote for this curve fx. If we take a very simple example, suppose we have this function fx and it is equal to 2x upon 1 plus x square. Now we have to find its horizontal asymptotes. So first we'll calculate this limit. Limit x tends to infinite 2x upon 1 plus x square. Now this is infinite limit. Degree of numerator is less than degree of denominator. That means value of this limit will be 0. In the same way, we'll calculate this other limit, which is limit x tends to minus infinite 2x upon 1 plus x square. It will also be 0. And when you'll study curve tracing, we'll draw this graph and you'll see that this graph will be drawn like this. So basically here the value of L and L dash is 0. So for this curve, this y equals 0 or x-axis is an asymptote. As you can see from the graph also, this line x-axis, it appears to touch this curve both at minus infinite and at plus infinite, and therefore it is a horizontal asymptote. And the second one is how to find vertical asymptotes. Now for vertical asymptote, we say that a line x equal to a is a vertical asymptote of a function fx if this limit x tends to a fx, it is equal to plus infinite, or this limit x tends to a fx, it approaches minus infinite, or any of one-sided limits also, it approaches plus infinite or minus infinite. Limit x tends to a negative fx, it approaches infinite, or this limit x tends to a negative fx, it approaches minus infinite, or this limit x tends to a positive fx, it approaches plus infinite, or this limit x tends to a positive fx, it approaches minus infinite. When any or both of one-sided limits, they approach infinity or minus infinity, then we'll say this line x equal to a, it is an asymptote to this curve. A very simple example is this function fx equals 1 by x. Now we know that it is not defined at x equals 0. Now if we take its limit at 0 negative, so this is limit x tends to 0 negative 1 by x. So it will be this limit h tends to 0 minus 1 by h. Now when h is 0 or 0 positive, then 1 upon 0 positive is minus infinite. So value of this function, it approaches minus infinite when x is 0 negative. Now if we take right hand limit, then we can write limit x tends to 0 positive 1 by x, and it will be this limit h tends to 0 positive 1 by h, and when h is 0 positive, 1 upon 0 is plus infinite. Here left hand limit, it approaches minus infinite, and right hand limit, it approaches plus infinite. So basically this limit, it does not exist, but still this line x equals a, which in this case is 0, x equal to 0 is a vertical asymptote. And if you recall the graph of y equals 1 by x, it is this graph. At 0 negative, it approaches minus infinite, and at 0 positive, it approaches plus infinite, and therefore this y-axis, which is x equal to 0, is a vertical asymptote in this case. Now when we will be studying curve tracing, we will be using these concepts to calculate horizontal and vertical asymptotes for rational functions. Here we will discuss a bit about asymptotes of a rational function. Now a rational function, it may have all three asymptotes. It may have vertical asymptotes, horizontal asymptotes, as well as oblique asymptotes. So first we'll discuss about rectangular asymptotes, and later we'll discuss about oblique asymptotes. We'll take up an example. Say for example, we are given this function fx, which is x square plus 3x plus 2 upon x minus 2, and for this rational function we wish to find out its vertical and horizontal asymptotes. Now for horizontal asymptotes, we'll calculate these limits. Limit x tends to infinite, x square plus 3x plus 2 upon x minus 2. Now in this case, power of numerator is greater than power of denominator. So when x approaches infinite, it approaches plus infinite. And since this value is not a finite value, we do not have a horizontal asymptote for x tends to infinity. Now if we look at this limit, x tends to minus infinite, it will be this x square plus 3x plus 2 upon x minus 2. Again here degree of numerator is greater than degree of denominator. So here it will be this minus infinite. So for this rational function, there is no horizontal asymptote. Now we look at its vertical asymptotes. Now for this function, we have x minus 2 in the denominator, which simply means that when x is equal to 2, this function is not defined. So it is not defined at x equal to 2. We find its left hand limit at 2. So its left hand limit at 2, it will be x square plus 3x plus 2 upon x minus 2. Now this is 2 minus h, so it will be this minus h and then this positive value. So as x approaches to negative, this value, it approaches minus infinite. And we find this limit x tends to 2 positive, it will be x square plus 3x plus 2, and this is x minus 2. Now in the neighborhood of 2, this numerator is positive, and this is 2 plus h, so it will be this h. So positive value upon h is simply plus infinite. So here we have left hand limit as minus infinite and right hand limit as plus infinite. So in this case, we have a vertical asymptote at x equals 2. Now for rational functions, there is a direct shortcut or a direct way to calculate oblique asymptotes. So here we'll calculate oblique asymptotes for this function. Now basically in rational functions, oblique asymptote, it will occur if degree of numerator minus degree of denominator, it is equal to 1. So this oblique asymptote will occur if degree of numerator minus degree of denominator is 1. So there is a difference of degree 1 between numerator and denominator. So if we have any rational function which is fx upon gx, and we know that degree of fx, it is suppose n, and degree of gx, it is n minus 1. So basically we can divide fx with gx using long division or synthetic division. So when we divide it, we can write this as y equals ax plus b plus some qx upon gx, where degree of qx now is less than degree of gx. Now when degree of qx is less than degree of gx, so if we take this limit x tends to plus infinite or minus infinite, in this case this limit qx upon gx, it will be 0. So this line y equals ax plus b, it will be an oblique asymptote for this rational function. So if we come back to our example, our function is y equals x square plus 3x plus 2 upon x minus 2. So if we divide, we can write x minus 2, and here it is x square plus 3x plus 2. Now this is x, this will be x square minus 2x. Now this is minus plus 5x plus 2 plus 5. So it will be this 5x minus 10, and this is 12. So we can write this as x plus 5 plus 12 upon x minus 2. Now if we take this limit, x tends to plus infinite or minus infinite, this expression will be 0, then it will be this straight line. So oblique asymptote for this function y equals x square plus 3x plus 2 upon x minus 2, it will be simply y equals x plus 5. So we have this oblique asymptote. So here in this case, we do not have any horizontal asymptote, but we have a vertical asymptote at x equals 2, and we have an oblique asymptote at y equals x plus 5. Now if we look at graph of this function in Desmos, then we can see there is no horizontal asymptote, as when x tends to minus infinite, this graph it approaches minus infinite, and as x tends to plus infinite, this graph it approaches plus infinite. So there is no horizontal asymptote. And at x equals 2, we have this vertical asymptote. So these two branches, on the left hand side this limit is minus infinite, and on the right hand side this limit is plus infinite. So we have an asymptote at x equals 2, and if we draw this line y equals x plus 5, it will be this straight line. So this is y equals x plus 5, which is the oblique asymptote for this curve. So this is how we calculate horizontal, vertical and oblique asymptotes for a rational function. Now we learn a general method to find oblique asymptotes. Now here what we'll say is, we'll say let the asymptote be y equals mx plus c for this function f xy equals 0. Now here we'll follow a couple of steps. First step is, we'll write this curve as this fn xy, fn minus 1 xy, f n minus 2 xy up to f1 xy plus constant term, say k equals 0. Now this fn xy, it contains all the terms whose degree is n. In the same way, this fn minus 1, it contains all the terms with degree n minus 1. Here, all the terms for this function with degree n minus 2. These terms, they will have degree 1, and this is simply our constant terms. And after this, what we'll do is we'll put x as 1 and y as m. And we'll write fnm. If we put x as 1, it's a function of one variable, so we'll write fnm. In the same way, we can write fn minus 1m, fn minus 2m up to f1m. So this is our first step. Now this second step is we'll take this function of m with highest degree n, and we'll find all real roots of fn m equals 0. So from here we'll get different values of m, and these are our slope of asymptotes. For an asymptote, we now have its slope. Next, we need to find its intercept. Now we need to find intercept of the asymptote, but this intercept, it depends whether from the second step we get a repeated root or a non-repeated root. So in this third step, first we'll consider all those cases where m is a non-repeated root. Now if m is a non-repeated root, then for this m we'll find corresponding value of c using this equation, which is c into f dash nm plus f n minus 1 m equals 0, where this f dash m, it is unequal to 0 since m is not a repeated root. So for all the non-repeated roots, the corresponding value of c is given by this equation, which is c into derivative of fn plus fn minus 1 equals 0 for that particular value of m. And once we have m and c, we can write equation of asymptote as y equals mx plus c. Now this second case is if m is a repeated root, or in this case it is a double root. Now if m is a double root, fn m will be 0 and f dash m will also be 0. In this case, we'll have two values of c, and these two values of c are given by the equation c square upon factorial 2 f double dash n m plus c upon factorial 1 f dash n minus 1 m plus f n minus 2 m equals 0, where second derivative at m for this degree n, it is unequal to 0. So for a double root, we have this quadratic equation in C, for which we'll get two values of C, and thereby we'll get two asymptotes as y equals mx plus c1 and y equals mx plus c2. Now for triple root, it will be c cube upon factorial 3, c square upon factorial 2, c upon factorial 1, and then it will be this third derivative, second derivative, first derivative, and f n minus 3. So this is how we can generalize this equation for any number of repeated roots. Now let us take up an example. Suppose the question is, find all the asymptotes of the curve x cube minus x square y minus xy square plus y cube plus 2x square minus 4y square plus 2xy plus x plus y plus 1 equals 0. Now we look at first 4 terms. All of them, they are of degree 3. So basically it is f3xy. Now next 3 terms, they are terms of degree 2. So this is f2xy and this x plus y is degree 1 terms and this is our constant. Now first step is we'll put x as 1 and y as m and we'll write f3m, f2m and f1m. So this f3m, it will be 1 minus m minus m square plus m cube. f2m will be, now this is 2 minus 4m square plus 2m. And here f1m will be simply 1 plus m. So all we need to do is we'll put x as 1 and y as m and then we have to write f3m, f2m and f1m. Now this second step is we'll find slope of the asymptote, and for the slope of asymptote we'll take this function with highest degree and we'll put it equals to 0. So we'll take this f3m, which is 1 minus m square plus m cube, and we'll put it equals to 0. Now this is 1 minus m and we'll take m square common and then it'll be this 1 minus m. So this is 1 minus m into 1 minus m square equals 0. So from here we can say value of m is minus 1, 1 and 1. So basically we have 3 values of m, of which this minus 1 is non-repeated root and this 1 is a double root or a repeated root. Now for these values of m, we have to find their corresponding values of c to find equation of asymptote, which is y equals mx plus c. So for this third step, first we'll consider the case when m is minus 1, basically which is non-repeated root. Now for this case, value of c is given by c into f3 dash m plus f2 m equals 0. And in this case, value of m is minus 1. Now this is c into, now what is f3 dash m? It will be minus 1 minus 2m plus 3m square. So that's your f3 dash m, and it will be minus 1 minus 2m plus 3m square plus f2m, and f2m is 2 minus 4m square plus 2m equals 0. Now if we put m as minus 1, it will be minus 1 plus 2 plus 3. So there will be 4c, and here it is 2 minus 4 minus 2. So minus 4 equals 0. So from here we get value of c as 1. And once we have m and c, we can write equation of asymptote. So for this case, equation of asymptote is given by y equals minus x plus 1 or x plus y equals 1. Now we'll come to the second case when the value of m is 1, which is a double root. So for this second case, value of m is 1, which is a double root, and for this case we'll have two values of c, and which will be given by this equation c square upon factorial 2 f double dash 3m plus c upon factorial 1 f2 dash m and plus f1 m equals 0, where the value of m is 1. Now this is c square upon factorial 2. Now what is f double dash 3? It is minus 2 plus 6m. So it will be minus 2 plus 6m and plus c upon 1. Now f dash 2, f2 is this function. So f dash 2m, it will be minus 8n plus 2 and plus f1m, and f1m is 1 plus m equals 0. Now for this we'll put m as 1. Now if you put m as 1, it'll be this c square by 2 and this is 4 plus c, and here it is minus 6 and plus 2 equals 0. Now this is 2, and if we divide everything with 2, we'll get this equation as c square minus 3c plus 1 equals 0. So from here we'll get the value of c as minus b plus minus b square minus 4ac upon 2a, which is 3 plus minus under root 5 by 2. So when the value of m is 1, we have two values of c, 3 plus under root 5 by 2 and 3 minus under root 5 by 2. So in this case, we'll have two asymptotes. So one of them is y equals x plus 3 plus under root 5 by 2 and y equals x plus 3 minus under root 5 by 2. So for this curve, we have three asymptotes. One of them is x plus y equals 1, and the one is y equals x plus 3 plus root 5 by 2 and y equals x plus 3 minus under root 5 by 2. So this is how we find all the asymptotes of a curve. So for this curve, we have three asymptotes. X plus y equals 1, y equals x plus 3 plus under root 5 by 2, and this third one is y equals x plus 3 minus under root 5 by 2. Now if we look at graph of this curve in Desmos, this graph, it looks like this. So basically it has three branches, and if we plot the asymptotes, this is how the graph will look like. We have this asymptote x plus y equals 1, and then we have this asymptote y equals x plus 3 plus root 5 by 2, and this other one which is y equals x plus 3 minus under root 5 by 2. So all these three lines, they are asymptotes to this curve. Now if we consider the case of a hyperbola, we can write x square upon a square minus y square upon b square minus 1 equals 0. In this, we have this term with degree 2. So this is f2xy, and this is our constant term. Now in this, we have our first step. We'll put x as 1 and y as m. So we'll write f2m as 1 upon a square minus m square upon b square. And here f1m is 0. Now second step is we'll find slope of asymptote, and for this we'll put f2m as 0. Now if we put it equals to 0, we'll get 1 upon a square minus m square upon b square equals 0, or value of m is plus minus b upon a, and both of them, they are non-repeated roots. And then we'll find its intercept. Now this is c upon factorial 1 into f2 dash m plus f1m, and it will be equal to 0. Now this f1m is 0. So from here we can say value of c is 0. So in both the cases, value of this intercept will be 0. So for this hyperbola, equation of asymptotes is given by y equals mx. So it will be this y equals plus minus b upon ax and plus c, which is 0. So this is how we find asymptotes of a hyperbola.